topic 4, lesson 2, which is on metals and metallic alloys. So we talked in the last lesson about all the different materials that are out there, basic idea. The big ones we're going to really focus on are these 6 main groups. So metals and metallic alloys, timber, which is all your different wood products, glass, plastics, textiles, and composites. And this chart shows 5, but it's really the same idea. There's probably something in there that's consolidated together. Okay, metals and metallic alloys typically are hard and shiny, like some of the examples you see on the bottom right there. Typically, they're good electrical and thermal conductors, but most of these pure metals are not super desirable. They're either too soft, too brittle, or too chemically reactive. So oftentimes, instead of using a pure metal, we mix them together, and that's called a metallic alloy. When we alloy metal, we are affecting their physical properties. And this is a good chart. It's rather simplified, but it gives you an idea of what it looks like. You can think of the atomical structure of these metals as almost looking like a crystalline structure where these are all organized in certain ways. Now they have some room to move, and that's why a lot of alloys can be malleable and soft, and you can hit them and they bend or dent. But what happens as you these are also referred to as a grain size. IB calls it a grain size. But what you do is as you're alloying these metals and you're mixing different metals together, their grains or their crystalline lattice or structures actually blend with one another. They overlap with one another. So where there may have been some gaps initially, they're getting filled by the grains or the crystalline structure of the other metals that they're mixing with. And in the end, what you can see if you start to mix multiple things together is it kind of gets chock full of stuff. And it's now not going to be as soft and flexible as it used to be. And maybe that is a desirable trait of your alloy that you're making. When we alloy, we can do a couple different treatments to it, and 2 that you need to be familiar with are work hardening and tempering. Work hardening strengthens. The strengthening occurs because of the dislocation movements within the crystalline structure of the material. You can think of this as the blacksmith working on a horseshoe back in the day, right? And he's got his horseshoe and he's heating it up in the fire, and then he's pulling it out and he's whacking the thing with a hammer. By hitting it with a hammer, you were causing a dislocation of this crystalline structure, and what that's doing is putting it into a non-optimal spacing. And then quickly when he's done, he'll take the horseshoe and he'll plunge it into the water to cool it down really fast and hold it in place. And that's called work hardening. Obviously, if you're making a shoe for a horse, you need it to be pretty hard. Now, sometimes if you have something like this bladed knife that you can see on the bottom left, sometimes you want parts of the knife to be harder than other parts of the knife. Maybe you want to reduce the hardness in some places. So what we can do there is we can do selective cooling. Instead of cooling the whole thing down really fast, we can selectively cool it. So tempering increases the toughness. Toughness means it's less likely to break. It also means it's a little more flexible because it's less likely to break now. So it increases the toughness of iron-based alloys, usually performed by after hardening, to reduce some of the excess hardness, because you don't want the whole thing to be super hard. It's done by heating the metal and then allowing it to cool slowly. Okay, that's going to allow it a little more flexibility versus the heating it up and plunging it into the cold water to cool it quickly. Metal extraction process. A lot of metals are still extracted this way. Basically, we find an area in the ground that is high in concentration of the metal that we're trying to get. In this case, I've got a picture of iron ore. So you're going to go dig iron ore out of the ground. You're going to put it into a large vertical, basically a large cylinder, like what you see on the right here. It's called fractionation chamber. And what you're going to do is when you heat it up, it's going to start separating into all of its different components. And iron, as it melts, is usually one of the most dense things in there. And you're going to see that the iron comes off at the bottom. Things that are less dense will be found higher. Gases will burn off. We feed air into it so things can combust if they need to. But you also get slag. And slag is just some of the other stuff that's in the ground that wasn't desirable. And we usually just dispose of a lot of it. It can be landfilled. Sometimes it can actually be put on farms. Super alloys. Okay, so super alloys are going to be elements or alloys that have certain resistance to undesirable things like creep and oxidation. Let's start with oxidation because it's just a big fancy word for what you would typically call rust. But when things oxidize, they're breaking down. So a super alloy is going to have resistance to rust. So you might think stainless steel, okay, versus just plain iron. When we make jets, jet engines get very, very hot. We have to use super alloys because we need to make sure that their structural integrity maintains itself even at really high temperatures. We can't afford for it to start getting soft and deforming. As far as creep, creep is change in position over time. Usually happens very slowly. It depends on the material. Now, here's a story I've heard, and I've had people tell me this isn't actually true, but it sounds really good, so I'm going to tell you anyway. And I'm not convinced that it's not true in some instances. If we look at stained glass windows, especially in really old cathedrals or structures that are hundreds of years old, what you see over time is that the glass will slowly creep down the window so that in each of these isolated panes, if you look at the bottom, it's going to be thicker in glass than what would be at the top of that because the glass very slowly over long periods of time is able to creep a little bit. That would not be a desirable trait for when you're designing a product. Recovery and disposal of metals and metallic alloys. So what I put here were a couple things as far as recovery. One of the things we can do is we basically take whatever the trash or the waste was, we break it up into as small parts as we can, and then we use magnetic fields, whether it's for the rare earth or for the ferrous materials in there, to then separate out what we have and we can isolate based on characteristics. This is from 2007, so it's a little bit older, about 13 years at this point. But what percentage of these different metals gets recycled in the United States? For some, like lead, it's quite a bit. And that's probably from lead batteries, lead acid batteries. But for some, like zinc and copper, we're not recycling them as well. International mindedness. Extraction takes place locally with added value often occurring in another country. So oftentimes the country that is having this huge mine pit that is probably degrading their environment to get down to these ores, oftentimes they're not making the big chunk of the money off of the product. The ores, once isolated, are then sent to other countries, oftentimes, and refined there. Maybe they have more technology to do so. So what IB is saying here is that even though maybe you have the gold mine, it doesn't mean you're making all the money from the gold. Aim 5. Design for disassembly is an important aspect of sustainable design. Valuable metals such as gold and copper are being recovered from millions of mobile phones. Some laptops and mobile phones can be disassembled very quickly without tools because they were designed for disassembly to make recycling more doable.